Bhim 8.8 Singular Value Decomposition. We have seen in the last video that if H is a complex Hermitian matrix, then H can be decomposed as P times D times P star, where P is unitary and D is diagonal with real entries. Now this holds when we have a complex Hermitian matrix. Now this result, which is called spectral decomposition or spectral representation, is extremely useful. So naturally people wanted to know if we can somehow generalize it that will hold for any matrix over the complex field. And by any matrix I mean not necessarily complex Hermitian, not necessarily even square. And quite surprisingly the answer turns out to be yes, and that is what we call singular value decomposition. Suppose I take any matrix A, m by n over C. Then I can always decompose it or factorize it as U times S times V star. Notice that U is a square matrix, so is V star, and S has the same size as the original matrix M, A, where U and V are both unitary matrices and S has this form. I call it a diagonal matrix, but it need not be a square matrix. So by diagonal I mean it is something. It could be this is larger or that is larger. I have just drawn something. But the diagonal entries are the only non-zero entries. But I have not drawn the diagonal all the way through. These are the only non-zero entries. They occur all at the beginning of the diagonal, followed by zero entries, everything else zero. And this is of some length. Suppose there are got R entries here, and all these numbers are non-zero. They are non-zero real number. Not only that, I will also say that they are strictly positive numbers. So if I call them S1 to SR, then each of those SIs are strictly positive. In particular, they are real numbers, strictly positive, and everything else is zero. So any matrix can be written in this way. This is called singular value decomposition, or SVD in short. These entries, these S1 to SR, they are called the singular values of the matrix A. So singular values are always strictly positive numbers. Now the columns of U are called singular vectors. To be precise, they are called left singular vectors because U is multiplying it from the left. Similarly, the columns of V, they are called the right singular vectors of A. Now the proof of singular value decomposition, namely every complex matrix of whatever size may be decomposed like this, that is pretty straightforward to prove, though the proof given in Bhim is quite counterintuitive. So we shall give a direct proof from first principles, and a pretty short one too. We start with this matrix A star A, which is n by n, and it is easy to say that this is a complex Hermitian matrix. So we can have its spectral decomposition, which basically splits it up as some V followed by a D, V star, where V is unitary matrix and the diagonal entries of D are all real numbers. Let's note the orders of these matrices. Now we shall notice that all the diagonal entries of D, they must be non-negative real numbers. So I already said that they are real numbers, but they are actually non-negative real numbers. In order to say this, we observe that all these diagonal entries are eigenvalues of this matrix A star A. As a result, we have this relationship for some eigenvector non-zero. We must have this, where D is any typical diagonal entry of D. Now what I shall do is I shall pre-multiply this with V star. So now it is actually a scalar quantity because it is 1 by something and this is something by 1. So the entire thing is 1 by 1. And I do the same thing here. D being a scalar, it comes out. So it is V star. And I immediately recognize this as the norm square of V. So this is a strictly positive number, V being non-zero. Now this one you quickly recognize as norm square of A times V. So here D is the ratio between two norm squares, and this naturally forces this quantity to be non-negative and actually strictly positive, because clearly AV is also non-zero, AV being just a multiple of this. So I would not say it is non-zero. So D is greater than or equal to 0. So this forces that D is greater than or equal to 0. It could be 0. It could be 0 or it is strictly positive. Now, if I write down all the diagonal entries as D1 to Dn and all the columns of V as this, then we know from spectral decomposition that this is an eigenvector corresponding to this eigenvalue for the matrix A star A. Now, I have seen that all these things are non-negative, so some of them are greater than strictly positives, the rest being 0. Without loss of generality, I can assume that the first few are strictly positive and the remaining things are 0. If not, just relabel them, call the positive ones D1 to etc. and push the 0 ones to the end, which is basically just permuting the entries of D and accordingly permuting the columns and rows of V star. So without loss of generality, I can assume that the first R entries, R diagonal entries of D are strictly positive and the rest are equal to 0. So we have this one, V, then this diagonal matrix which has only R many strictly positive, everything else 0, and then V star. And it is easy to see that this R has got to be the rank of this matrix, because the rank of D is precisely the number of non-zero diagonal entries, and these being non-singular matrices, multiplication by them has no effect on the rank. So we have this directly from our spectral decomposition together with a little bit of permuting things. Now remember that this is what we are trying to achieve. A is equal to U d V star. So I am going to construct U, or rather I wrote it as U S V star for singular values. I have to give you U, S and V, then show that this result holds. So this is my step 1. I will take precisely this V as that V. Now a couple of points are to be noted here. If I consider the columns of V as V1 to Vn, then I know that for all I, A star A, Vi is di Vi, which basically says that this is the eigenvector corresponding to di. We have also said for all I less than or equal to R, the di's are strictly positive, the remaining di's which are just actually equal to 0. So for I greater than R, A star A Vi is equal to di times Vi, but di is being 0 here, I have only 0. Now from this there is an interesting implication. What I will do is I will pre-multiply this with Vi star. This of course keeps this 0, now it becomes the scalar 0. So this is nothing but norm square of AVI. So from this I conclude that AVI is equal to the 0 vector whenever I is greater than R. This fact is going to prove useful pretty soon. Okay, so now I'll give you how to define your S. Remember that the S matrix is like this, where this has the same order as the A matrix. So maybe this is smaller, maybe this is smaller. I have just drawn something, but part way through the diagonal you have some strictly positive entries. I am going to define them in the following way. For all I less than or equal to R, I will take them to be positive square roots precisely of these di's. So I know that these are all strictly positive. So those are my S1 to SR. So that finishes definition of S. So I have given you V, I gave you S. Now I am going to give you U. For all I less than or equal to r, I define my vectors ui as a vi divided by si, and you can see quite easily that these things are all m by 1. So I have given you exactly r vectors, and they are going to create part of my u. Remember, my u here needs to be m by m. And these are going to be the first r columns of u. I am going to give you the remaining columns in a moment. But since A has to be unitary, I just cannot give you any m columns and claim that they are the first r columns. So I have to show that all these things have unit norm, and these things have got inner product 0 between each other. To see that each of them has unit norm, I will consider this. This is norm square of ui, I going from 1 to r. Directly using this definition, I get this, si being a real number, complex conjugation does not change it, so I get this. Now I notice that S star a vi is, that is precisely di vi. Since the di's are scalars, I am just writing them at the end, so it is vi star vi. Now remember, V was a unitary matrix, so all the lengths of each columns must be 1, so this quantity is 1. And what is si squared? That is precisely di, so this also cancels nicely, so you are left with the answer 1. So all these ui's are indeed unit vectors. Next, I need to show that these r vectors are mutually orthogonal. For this, I work with ui star uj for I not equal to j, both of them between 1 to r. Then again, proceeding just as before, using this definition, I get, now here I can see S star a vj, that is just dj times vj, because this is an eigenvector, so I will just erase this and write dj. Now dj being a scalar may be written outside, so it is just basically the dot product of vi and vj. Because v is a unitary matrix, so its different columns are mutually orthogonal, so this fellow is 0, pulling everything down to 0. So I have shown that these r vectors that I created, they form an orthonormal set. Now if it is an orthonormal set in Cm, I can naturally extend them to an orthonormal basis of C to the power m. And that gives me my matrix U. I will take them as columns to get a matrix, and that will be my U. So I have given you all the ingredients now. I have given you a V, I have given you S, I have given you U, and by the very way I gave them, you already know that V is a unitary matrix. I know U is a unitary matrix because unitary means columns form an ONB. That's precisely how I constructed them. I already know that S is a matrix of the same size as A, with its first r diagonal entry strictly positive, everything else being 0. So the only thing that now remains to be shown is that A is indeed equal to this U times this M, S times this V star. Before I do that, let's take a quick look at the number R. This R, if you remember, was the rank of the matrix A star A. Now A star A was a matrix which was of the order n by n, therefore R is less than or equal to n. Now one might actually prove, by considering rank of this matrix and comparing it with rank of A star, that R must also be less than or equal to m. But however, we shall keep our proof simple, so I shall assume, without loss of generality, that n is less than or equal to m. Remember, this was completely arbitrary, so we are doing the proof for matrices which look like this. They might be lying down and not matrices like this, because once you finish proving for all matrices like this, you can directly take just conjugate transpose and get the corresponding result for this. So without loss of generality, I can put this assumption. It will make the proof easier. So immediately I get that R is also less than or equal to m. I can get this even without this assumption, but that just adds a few more steps. So I have given you the matrix U, the matrix S, and the matrix, well, call it V for the time being, that is the V matrix. And I know that S has these entries strictly positive, and there are exactly R many of them. Now we shall partition this matrix in a particular way. I start with S. I will partition it like this, this, and this. So this is the only non-zero part in the matrix, which I shall call S1. This is 0, this is 0, this is 0 of appropriate orders. Understand that S1 is an R by R matrix, which is non-singular because all its diagonal entries are non-zero, in particular strictly positive. Similarly, I will partition this fellow as the first R of them. I will call this as U1, and whatever comes after, I call that U2. And similarly, I shall split V again as the first R. I shall call it V1, and whatever comes after that, I shall call V2. Now quickly recall how we obtained U. We had first obtained the first R columns, then extended it to an orthonormal basis. So you obtain U1 from directly this V1. We had this relationship for I, all I less than or equal to R, Ui was AVI divided by SI. Now this may be written nicely in the form of a matrix like this. I can write this U1, so all the columns put together, that is A times V1. Then I have to divide the ith column by SI. So just understand that this is nothing but S1 inverse. You might need to think about it for a little minute to understand that these and these are just equivalent, because the inverse of S1 is simply a diagonal matrix with the ith diagonal entry given by 1 over SI, like this. So I can bring this S1 inverse to this side as S1 to get. Now I have to work with my entire U and not just U1, but that is not a problem because I can put this U2 here as long as I pad S1 from below with 0. So when I do the multiplication, it is U1 times S1 plus U2 times 0. I do not care what U2 is. I really do not care how I extended my orthonormal set to an orthonormal basis. So this part is basically uninteresting. It will get multiplied with 0. Notice that I have grown U1 to my full U. I have grown this S1 to this part. I have not yet grown it to that, but I have grown it up to this. So I already get that this is my U. Now I plan to grow V1 similarly into V1, V2. So what I shall do is I shall put my V2 here and just notice that whatever I am appending is nothing but 0. It is here that my old observation will come into picture. So this is one fact that I have proved right at the beginning, that for all I greater than R, AVI must be the 0 vector. Now in terms of matrices, this is actually AV2 is the 0 matrix. So if I want to grow this V1 into V1, V2, the extra thing that I will be appending when multiplied by A will give me just the 0 matrix. So if I consider A times V1, V2, A just enters AV1 times AV2, which is simply the 0 matrix. Now AV1 is this, so together I get EU, and this 0 thing I append at the end, I get S1, 0, 0, 0. So I have completed growing my S1 into S. So this is nothing but U times S. So I get AV is equal to US. Now I know that V is a unitary matrix, so it is invertible and its inverse is given by its star. So US V star, and that is precisely what I wanted to show. So this proof is directly from the first principles, and actually it gives you a way to construct them. You just start with a spectral decomposition of A of A star A, and then you actually construct your matrix U and matrix S. So this is a very basic result. So here as a summary, you can see that the way we constructed V, the right singular vectors, that is columns of V, are actually eigenvectors of A star A. So its eigenvectors make up the columns of V. Similarly, if I consider A star, it is pretty trivial to check that its decomposition, spectral decomposition, will be given by the other thing. So its eigenvectors are precisely the columns of U. And both of them have the same non-zero eigenvalues, and they are strictly positive. Their square roots are precisely the diagonal entries, the non-zero diagonal entries of S. So this is the spectral value, the singular value decomposition.